Hello, everyone. Welcome back. So, today we're going to be talking about the normal approximation to the binomial distribution. So, let's review what is the binomial distribution. The binomial distribution occurs when an experiment is repeated and each trial is an independent event, where each trial is considered a success, which has probability p for one success, or a failure, which is probability q for a failure. And failure and success are the opposite, so p is equal to 1 minus q, and vice versa. Q is also equal to 1 minus p. So, if you recall, we've actually already done an entire lesson about this earlier on in last unit. So, if you don't remember what binomial distribution is, go back and review that one. But basically, I hope this jogs your memory. It looks like this. Okay, so that's what it looks like that. And I go into detail in the previous lesson explaining why this is the way it is. And so, again, if this is not something you're familiar with, go and watch that one, as I'm not going to go into much detail about it here. And so, let's review one example though with binomial distributions. This one here says a coin is flipped 40 times, where a flipping a head is considered a success. What is the probability that a heads is flipped less than 25 times? So, how would we do this? Well, how would we do this? That's a great question. How we would do this is we'd say, well, what's the probability x is less than 25? And we calculate the probability that it's exactly 0, plus the probability that it's exactly 1, plus the probability that's exactly 2, and so on. All the way until we get up to probability that x equals to 24, right? Because it's got to be less than 25. The other way to do this is we could add up the converse, so everything, probabilities from 25 up to 40, which actually would be a few less probabilities, and then do one subtracted from from that number, and we would get the answer. However, calculating all of these or even all of those would be very, very time consuming, right? That's not really going to make sense for us to calculate all those. And so that's where the normal approximation to the binomial distribution kind of comes in, right? And so it says here that if a binomial distribution is graphed and satisfies the conditions that n times p is greater than 5 and n times q is greater than 5, then it would look like a normal distribution. So that's something to remember. How do we know that we can use this method, this normal approximation method for a binomial? Is does n times p equal something greater than 5 and n times q. Now, in this situation here, I bet we could use it, right? Because p is a half, right? Because remember, p is just the probability of one success, which would be a half, because a success is defined as flipping a heads, and there's a 50-50 chance that we'll get a heads versus a tails, right? So there we go. That's good. Okay. And then what is n? N is 40. N is 40. And so NP is equal to 1 half times 40, which is 20, which is certainly greater than 5. And NQ is also 1 half, right? Because Q is a half times 40, which is also 20, which is also greater than 5 once again. And so therefore, this is an example where we have enough, we have a high enough expected values for the failures and the successes that we're able to use this normal approximation. Okay, so what does this say here? It says if a binomial distribution is graphed and satisfies these conditions, then it would look like a normal distribution or a bell curve. A normal distribution that would be the same approximately as the binomial distribution would have these values. The mu would be NP, which that should be no surprise because the expected value is n times p. And we know that the expected value is the same as the average, right? That's what's going to happen on average. What do we expect to happen if we haven't actually done any trials, right? And then the standard deviation would be the square root of NPQ, right? Because the variance is just going to be NPQ. And so standard deviation is the square root of NPQ. Very good. So now that we know about this, now that we know we can use this in order to find the answer here, we're going to say, we're going to go and revisit this question we just did, where we have a coin that's flipped 40 times, and flipping a heads is considered a success. Use a normal approximation to find the probability that a heads is flipped less than 25 times. Well, what is that going to be? Well, the probability of x being less than 25.5 is going to be equal to the probability that z is less than some number. So what we need to do is we need to find the z score that corresponds with this value, right? So let's find mu, let's find the standard deviation, and then therefore let's find the z score, right? We know the z score is the x value minus mu over the standard deviation. And so if we can find mu and the standard deviation, right, mu and sigma, and we can also find the z-score, and then we can look the z-score up on the z-score table and find the answer. We'll be golden. We'll be good to go if we do that. Okay. All right, so let's do that. So mu is n times p, which actually we already found out before, but I'll write it again. It's going to be 20. And then standard deviation is root of npq. So that's a half times a half times 40, which is root 10, right? Yeah, that's going to be root 10. So therefore the z-score is x, which is 25, right? That's what we're trying to look for, 25. We're going to say, let's see. Yeah, so 25 we're going to subtract 20, and we're going to do that over the standard deviation, which is 10. So there we go. Okay. And what's that going to be equal to? Well, let's see. What is 5 divided by root 10? Is equal to about 1.58. Okay, so that's what we must do. We must figure out what is the probability the z-score is less than 1.58. So let's go do that. Let's go to our z-score table and figure that out. Okay, so 1.5 is here, and where is 8? That's here. So there we go. It's going to be 0.9429. Okay? 0.9429. So that seems to me like that's pretty likely, right? And if we think about it, that makes sense because the number we're expecting mu, right, is 20, and so for the head to be flipped 25 times, or not 25 times, but less than 25 times, seems pretty likely, especially when the standard deviation is only, what's standard deviation? This would be just more than 3, and so if we think about it, you know, how many standard deviations away from the mean do we get before we get pretty much all the data, right? It's not that many. Once we get to 2 standard deviations away, we're already at 95%. And so considering that, this really isn't all that surprising. Good. Very good. Okay, let's move on to another example here. Example 2 says, a spinner made of 5 sections labeled 1 to 5. The probability of section 1 is 10%, section 2 is 20%, section 3 is 30%, section 4 is 30%, and section 5 is 10%. If the spinner is spun at 20 times, can a normal approximation be used to find the probability that the section 3 will result 8 or fewer times? So let's ask ourselves that. First, we need to find NP and Q and find out that NP and NQ are both greater than 5. So let's first find n. Well, it says that the spinner is spun 20 times, so n is 20. P is the probability of 1 success. So in this case, we want to find the probability that section 3 will result 8 or fewer times. So we're going to define spinning section 3 as a success, right? And spinning section 3, it happens 30% of the time, so the probability is 0.3. And now the probability of a failure would just be the opposite. So everything that is not a success, So that would be the other 0.7, right? 1 minus 0.3 gives us 0.7. Now we need to calculate NP and NQ and figure out the answer. So what's N times P? That's 20 times 0.3, which is 6. And what's 20 times 0.7? That is going to be 14. Now both of these are greater than 5, and so therefore, yes, the normal approximation can be used, right? Now let's say these were not both greater than 5, then we would be saying no, the normal approximation can't be used. Now, given that this is a lesson all about the normal approximation, it makes sense that they probably wouldn't give us a question in this section where the answer would be no, it can't be used. However, on a test or on an exam, especially on a cumulative final exam where there's going to be questions possibly about this and also possibly just about regular binomial distributions, it's important to check, make sure you get it right, especially then because, you might be given an example possibly where the answer is no, a normal approximation can't be used. We've got to just use our regular binomial distribution principles that we know. Okay, very good. So what we're going to do is we are going to figure out mu and sigma, and then we're going to find this solution. So let's do that. Mu is n times p, which actually we already found out that's 6, so I'm just going to copy that from above. We already know that. And then sigma is the root of npq, so that's going to be equal to 20 times 0.3 times 0.7, and all of that square rooted. That's going to be 4.2. And so if we square root 4.2, we get about 2.049. So I'm just going to round to 2.05 there. Awesome. Okay, and we would like to know what will happen if we get 8 or fewer times. So in this case, because we're working with discrete data rather than continuous data, we're actually going to go up a half. Oh, and actually that's something I should have done previously. For this one, actually, instead of saying 25, technically it would have been slightly stronger. I know this is an approximation anyway, so it doesn't matter a great deal, but it would have been even stronger had I said 24.5 here for less than 25, because by going right up to 25, given that it's discrete, I'm not going to get as accurate of an answer because, 25 is a specific value that we could actually get, right, in discrete. Whereas 24.5 is not, right? It's halfway between two values we could actually get, one of which we want to include, which is 24, and the other of which we don't. So I'm going to do this here. I'm going to do this a bit of a stronger way here. And we're going to say that if we want a probability that x is less than or equal to 8, because 8 is included, we're going to say that's equal to the probability that it's less than or equal to 8.5, because 8.5 is not actually a value you could receive here, where it's either going to be 8 or 9. And we want to include 8, we don't want to include 9. And so by going up that half, given that we're applying something discrete to a model that's used for continuous, this is just going to give us a little bit more of an accurate approximation here. And so it's you're still going to get something relatively good, without doing this. However, going up that half step is going to get you an even more accurate result for that reason. Okay, so let's continue. So x is equal to 8.5 in this case. So the z-score is going to be 8.5 minus 6, right, minus mu, over standard deviation of 2.05, and that's going to be 1.22. So we want to know what's the probability that z will be less than 1.22, or less than or equal. Now we're switching to z-scores which are continuous, and so it doesn't actually matter here, whether we include the equal, the less than or equals, or just less than or not. Okay, so let's find that. Let's find 1.22, 1.2, and another 2. Okay, it's going to be 0.8888, so about 89% approximately. Oh, Next one. Okay. 0.8888. And that's what we expected if we think about it, right? We're spinning the spinner 20 times. And we're expecting about 6, right? We're expecting about 6 section 3s out of those 20, right? And so because we're expecting about 6 and we're wondering about 8 or fewer, then that's pretty likely to happen, right? That goes in and around all of those most common values that we're going to get, and also some less common ones that add a little bit more to that probability as well. And so this is about what we expected. We expected this to be relatively a likely thing to have happen. Good. And also standard deviation, it's 2, right? It's 2.05, and so 8 is about 2.05, just a little bit more than 2.05 above. So we're getting almost to that full 1 standard deviation from the mean, which already means we're going to get about already automatically 68, right? Already at least 68, and then also a bit more than 68, about halfway between 68 and 100 approximately in that case, because we have the two sides. One of them we get and one of them we don't. So so long story short, that's about what we expected. Letter C asks, what is the probability that a section 3 will be the result exactly 10 times? Okay, so in this case, although we could use the approximation, we don't have to. I'm going to here because I know that that's what this lesson is about getting used to using it, so let's do that. So the probability that x is equal to 10 is equal to the probability that it's between 9.5 and 10.5. Now you may argue, oh hey, but wait a second, because it's discrete, it's also the same thing as the probability of being between, 9 point why can't we use like 9.75 and 10.75 or something like that? And that's because it's not an equal distance between. We want something that's an equal distance between that best represents that 10, but also without going so far out, right? We wouldn't want to do 8 and 12, for example, even though those do have an equal distance to 10, because then we're getting then we're getting into other territory with other numbers as well. So that's why we like to do just 9.5 to 10.5 to best represent 10. That's kind of my long story short version as to why that is. So that's what we'll go with today. Good. So in this case, we want to know the probability that we're less than 10.5 minus the probability we're less than 9.5. And why is this? How did I get from step 1 to step 2? Well, let's talk about that. So let's say here, for example, we have our scale, and let's see, what was our mean? Okay, our mean was 6. I want to draw this somewhat accurately, and not just completely approximate this. So here's 6, and let's say it's 2, 2, 2, 2, 2, 2, 2. It's a little more than 2, but this is an approximation here. 4, 0, 2, 0, and then everything here we don't have to worry about because we can't really get less than 0. But anywho, here is our mean, right? Here is our mean for this. And what I want to know is between 10.5 and 9.5, so right around that mark of 10, right? 10.5 and 9.5. I want to know this area. So if I take this entire area, everything that's below 10.5, and then I subtract off everything that's below 9.5, so all of this area gets subtracted off, and it's gone, what am I left with? I'm left with just this area here, right? I'm left with just that little green area there, right? That's all I'm left with, and that's what I want. That is my goal in this entire thing. Good. So let's see. What are our z-scores? Well, our z-score for 10.5 minus 6 over 2.05. And I'll put in brackets, this is an approximation. I mean, this whole thing is an approximation, but this is an approximation. I didn't really properly do the 2.05. I just, rounded to 2 there. This is going to equal to 2.2. And our z-score for 9.5 is going to be equal to 1.71. So essentially what we want to know is what is the probability that z is less than 2.2 minus the probability that z is less than 1.71. Well, let's go to our z-score table and find out. So let's flip a few pages here. All right, so what was our first number? Actually, I'm going to clear all this. These are from previous times. The first one was 2.2. So let's see, 2.2 is right here. So that's going to be 0.9861. The other one was 1.71. So here we have 1.7 and then we have a 1 there. So that's going to be 0.9564, right? And it makes sense these are both relatively big numbers, right? Because here one of them we're taking most of the graph as we saw in that graphical representation, and the other one we're just going a little bit over and then, subtracting most of that same thing back again. So we know this is going to be a relatively small chance when we're only going with one number here. Good. So this is going to be equal to 0.9861 minus 0.9564, which were those numbers we found. And that's going to end up giving us 0.0297, so just shy of 3%, right? And that makes sense because, what's the probability this will happen actually exactly 10 times? So no more and definitely no less, right? Most of the time when we have a mean, especially a mean of 6, then it's going to be less, especially our standard deviation is 2. And so 10 is almost 2 standard deviations away from that mean. That's pretty far. And so even though it's possible that it happens, it's not that likely to happen, unfortunately, right? Or perhaps fortunately. I don't know whether we want section 3 or not, whether that's good or bad, but regardless, it's just not that likely to happen. And so we expect it to not be that likely to happen. All right, well, with that said, that is it for the binomial or the normal approximation to the binomial distribution, which is a great topic. Next time, we're going to be talking about repeated sampling and hypothesis testing, which is very much a new topic that I don't think a lot of us have heard of yet, but we'll talk about it next day. So have a great rest of your day, everyone, and I'll see you next day for hypothesis testing. Bye, everyone.